Keynote 3, last day of SoCC. My name is Shahram Pandaharizadeh, and I'm the chair of this session. The presenter of this session is Professor Juliana Ferreri of NYU, and the title of her talk is Towards Usability, Interactivity, and Trust for Data-Intensive Computations. So Juliana Ferreri is a professor of computer science and data science at New York University. She's the elected chair of the ACM Special Interest Group on Management of Data, SIGMOD. In other words, she's one of my bosses as the steering committee chair. She served as a council member of the Computing Research Association's Computing Community Consortium and was the lead investigator and executive director of the NYU Moore Salone data science environment. Her research interests are in large-scale data analysis, curation and integration, visualization, provenance management, and information discovery. She has made contributions to data management methods and tools that address problems introduced by emerging applications, including urban analytics, predictive modeling, and computational reproducibility. Professor Ferreri has co-authored over 200 technical papers, including 8 award-winning publications, several open source systems, and is an inventor of 12 patents. She's an ACM fellow and a recipient of an NSF career, 2 IBM faculty awards, and a Google Faculty Research Award. She was recognized with the ACM SIGMOD Contribution Award in 2020. Congratulations. She received her bachelor's degree in computer science from Federal University of Brazil and MSc and PhD degrees in computer science from the State University of New York at Stony Brook. So without any further delay, Juliana, welcome, and please give your keynote. Thank you.
Thanks, Sharon, for the kind introduction. I'd also like to thank Rodrigo, Christina, and Bang for inviting me. It's a great honor to be here. And thank you all for being here from all the different time zones in the world. So as Sharon said, today I'll be talking about the pressing need that we have right now to democratize data-driven exploration and present some of the work that we've done in this direction. So we've all witnessed, a revolution in the way that data-driven exploration has impacted our society, right? In science, it has led to great advances and discoveries, and it has also transformed how science is done. In addition to hypothesis-driven research, scientists now engage in what is called data-driven hypothesis-generating exploration. And Jim Gray called this shift as the fourth paradigm. Companies are also capitalizing on data. In fact, for many businesses, the main source of revenue comes from data they collect and sell, right? So some have even referred to data as the new oil. And last but not least, governments are increasingly collecting troves of data and using these data to improve their operations, to make policies, and we hope make informed decisions, right? So we've seen a perfect storm, and what has enabled this revolution is the fact that now we have computing and storage that are essentially free, right? Data are abundant. And the problem we have now, the challenge that we have is that the bottlenecks to all these great things lie primarily with people. So to look at a concrete example of both the opportunities and challenges of data-driven exploration, let's consider one specific application area that I've worked on, which is urban science, right? So cities are the center of economic activity, and today more than 50% of the world population lives in cities, and this number is slated to grow to 70% by 2050. And since all of us that live in cities or that visit cities, we see that this growth leads to serious problems around transportation, resource consumption, housing affordability, as well as inadequate or aging infrastructure. But there is a light in the end of the tunnel in the sense that lots of data are now being collected about many cities. And not only data are being collected, but they're being made openly available in many different portals throughout the world, right? And these data are being collected about the different components of urban environments, the infrastructure, environment, and the city residents. And the question that we have before us is, can we leverage the data exhaust from these different urban components to crack the code of cities? Can we better understand how these different components interact over space and time and use these insights to make the cities more efficient, sustainable, and more importantly, improve the lives of their residents? So the answer is yes, and there are a number of success stories that were born out of the use of urban data. And here are a few of these. One is, the use of historical and real-time bus information to provide users, bus riders, real-time bus arrival predictions. And this is an example where you can use data to directly benefit residents. There are also another example that I like to use is, this effort here in New York City, where a team from the mayor's Office of Data Analytics, combine information from multiple agencies and created a predictive model with the goal of improving the hit rate for their inspections for illegal conversions, right? And this is an example where you use data to make cities more efficient and indirectly benefit their residents, right? And the last example that I have here is one of a study that was done here at the Furman Center at NYU, where they show that a high increase in foreclosures leads to upticks in crime. And this is an example where data was used to impact policy because based on this study, the NYPD actually updated its policing strategies, right? So we see that there is great promise. And one question that we may ask is, why don't we have more success stories, right? Even though we have some, they're few and far in between. And all of these that I mentioned are one-off efforts that have required substantial resources, right? So the question is, why don't we have more of these success stories? And the answer is that it's hard, it's difficult. Exploring these data is difficult. First and foremost, data are vast and they are produced at very high rates. Sorry, hello?
I can hear you, Juliana.
Oh, somehow I think that my connection stopped. Can you see my screen? No, right?
No. Presentation.
Yeah, so my screen, go ahead.
Do you have to reshare again?
Okay, I'll try. Yeah, my screen started flickering and can you see it now?
It's coming back. Yes, we can.
Okay, my apologies. I don't know what happened. Right. So as I was saying, the problem is that exploring these data and getting insights from these data is very difficult. First and foremost, these data are vast and produced at a very high rates from many different sources. And they come with different levels of reliability. And they're very difficult to combine and integrate, right? Not only that, in order to extract these insights, you need to assemble complex computational processes that require expertise in different topics, from data cleaning, data management, to visualization and machine learning, right? And now we have a broad range of users or data enthusiasts that are actually trying to do this. And many of these do not have any training in computing. So if assembling these computational processes is difficult for us that are computer scientists, it's next to impossible for experts that do not have our training, right? So it's difficult for them, for these domain experts that actually understand to export the data, because they have to rely on data scientists or computer scientists, and this hampers their ability to actually explore and obtain insights from the data. And this problem is compounded by the fact that the exploratory analyses are inherently iterative, right? As you test and test your hypothesis, as you come up with new hypotheses, right? You can start with some data, you do some computation, you generate results, you try to understand those results, you come up with new hypotheses, new questions, you change your computation, you can keep doing this iteratively until you either hit a brick wall or come up with your aha moment, right? I discovered it. And the challenge here is that after many steps, there are many ways in which you could have been wrong, or the data that you use could have been wrong, right? And the big question is, in this tortuous path from data to knowledge and eventually decisions, right? There's problems can happen and things can go wrong. And the question is, and the problem is that in this day and age where increasingly decisions are based on data and computations, incorrect conclusions can lead to bad decisions that have serious consequences. Right? So my research over the past many years has this overarching goal of empowering a wide range of users to explore and obtain trustworthy, actionable insights from data, right? In our group, we develop methods that address problems at different stages of the data lifecycle, from data discovery and search through curation, data management, analysis and visualization. Okay. Hello?
We can still
Sorry.
see,
Yeah.
but not
Yeah.
your presentation, Juliana.
Sorry. There's something wrong going, I think, with probably with my computer. Let's try if it goes bad again. I'll try to find another machine. But as I was saying, so we work on methods for the different stages of the life cycle, from discovery to curation, data management, analysis, visualizations, machine learning, as well as methods to support this data life cycle, including methods for provenance and reproducibility and debugging and trusting these computations. And oftentimes the problems we work on are actually motivated by real applications, and some of the application areas I've worked on include urban science, misinformation, and scientific reproducibility. Okay, that's all right. So, as you can see from the different conferences that we publish in, our work often combines methods from different computer science areas to solve these real problems. And we also build systems that are deployed and that are used by domain experts. And I'm very fortunate to be part of the VIDA Center, the Visualization, Imaging, and Data Analysis Center at NYU, where I collaborate with a number of researchers from different areas that all share with me the passion of solving data, using data to solve real problems, right? And whose contributions have enabled much of the work that I'm gonna talk about today. And I have to thank them a lot because I've learned a lot from them. All right, so let's go over what I'm going to be talking about today. I debated a little bit about what projects I would discuss, and I decided that these two would probably be the most relevant for the SoCC attendees. And these are, the issues of usability and performance to enable interactive exploration, and reproducibility and trust, how do you support reproducibility and trust for computational pipelines? So let's start with the first part of the talk, which is on usability and performance. And I'd like to show you a short video that demonstrates a system called Urbane that was developed by folks in my group in collaboration with architects from KPF. So let's see.
Urbane allows users to seamlessly explore the city based on multiple 2D and 3D data layers. For example, noise, crime, and is visualized here, subway access. The data can be explored at different resolutions. The city...
We lost your
Okay, so let me try to see if I can deal with this, because it might be a problem. Sorry. Sorry, let me see if I can fix the screen. Okay, let's try once more. My apologies.
Urbane allows users to seamlessly explore the city based on multiple 2D and 3D data layers. For example, noise, crime, and is visualized here, subway access. The data can be explored at different resolutions. The city, neighborhoods, and buildings. The opacity of the 3D buildings can be controlled for better visualization of the data layers. Urbane uses a parallel coordinate chart that allows for easy and intuitive filtering of urban datasets. Here we filter neighborhoods for various attributes such as subway access and noise. The bold blue line represents the average of all Midtown neighborhoods. The bold red line is a user-selected neighborhood, here the financial district. Filtering of various attributes allows users to understand the characteristics of Manhattan neighborhoods. For example, the financial district and Midtown are very similar across most attributes. At the neighborhood scale, the same filtering system is applied to individual buildings. Again, the blue line represents the Manhattan average. Here, we filter individual buildings for attributes such as built area, crime, and noise, identifying sites for potential development. Once specific sites have been identified, Urbane gives users the ability to replace existing buildings with new buildings, testing different tower sizes and program combinations for the maximum zoned floor area. The user can generate speculative buildings on many sites. Here we see a hotel with residential, an all-residential building, and an office with residential. Once buildings are generated, Urbane can compute derived 3D attributes from the data in buildings. This includes the view from buildings to selected landmarks, the impact of buildings on sky exposure at the street level, and the impact of the buildings on the views of the existing context. This analysis can be used to evaluate the trade-offs between the value of a new development and its impact on the character of the neighborhood. This can facilitate the design and development process between architects, developers, and city planners.
Okay, so I hope that so I see Urbane as a visual analytics. It's a visual analytics system that was designed for use by architects, and it supports very complex explorations that take into account the three-dimensional aspects of urban environments, right? And the architects are able to perform this analysis very easily through this point-and-click interface. Right, some examples of 3D queries that they can pose that were shown in the video include these view impact queries, as well as sky exposure, right? But users can also explore the data in a two-dimensional fashion, right? The two-dimensional data. And again, they can do that using visual queries, right? So instead of writing SQL queries like these spatial aggregation here, they can see the equivalent heat map that shows, the density of taxi pickups in different neighborhoods in New York City, right? And also they can compare different neighborhoods or different regions through these parallel coordinates, which essentially is, for each of the coordinates here, right, corresponds to one of these queries over a different data set, right? So, through the design of, the appropriate visual representation and interactions, you can actually enable experts that do not have training computing to perform rather complex analysis, right? But then we have one big challenge. And the challenge is that how do you attain interactivity? And in their paper from 2014, Lee and He report the results of a study where they show that increased latency, even a 500 millisecond difference, greatly reduces the rate at which users make observations, draw generalizations, and generate hypotheses, right? So for such visual analytic systems, it's critical that we support interactive query response types. But this is challenging here, in particular because in such systems, every interaction leads to a potentially large number of queries. We have a high query rate, right? So one query can be expensive. Dealing with lots of queries in real time is even more difficult, right? And Urbane has a particular challenge here because it makes heavy use of spatial aggregation queries, which are notoriously expensive to compute, right? So if we look at the plan derived by a commercial spatial database, right? So this is how this query is actually evaluated, right? So first you have to join the taxi trips, right? So if I want to find the count of taxi pickups in all neighborhoods in Manhattan, right? I have to start by doing a join between the taxi pickups, the taxi trips, and the set of New York neighborhoods. And this join is done actually in two stages. In the first stage, there's a filtering step where the neighborhood polygons are actually approximated by a minimum bounding rectangle, an MBR, right? And that filters the points that are in that MBR. And then in the second step, you need to do a refinement where you actually need to check for the points that lie in the MBR, the ones that actually lie inside the polygon, right? And this is what is called the point in polygon test, right? And because real world regions are fairly complex, if you look at these polygons for Manhattan neighborhoods, they can have hundreds of vertices, right? This point in polygon task can be very time consuming because each task takes time linear with the number of vertices in the polygons. And if you think about the size of the data set that we have here, billions of points, this can be extremely expensive, right? Finally, another bottleneck that you have when you're trying to evaluate these queries is the fact that the relational databases require the results of the join to actually be materialized before the aggregation is computed, right? So this adds to the query evaluation time. And just to give you an idea, for this particular query using a commercial database, it took several minutes to actually derive the answers. Right. So you might ask, how did we did this, the magic with Urbane, where we can answer a large number of these queries with interactive response times? And the answer is that we took a fundamentally different approach to evaluating the query and considered spatial aggregation from a geometric point of view, right? So instead of thinking about the query plans, joins, and aggregations, we view a spatial join between a point data set and a polygon data set as just drawing these points and polygons into a canvas and examining their intersections, right? So this is very simple, and this is essentially a rasterization, which is a basic operation that is supported natively in graphics hardwares in GPUs, right? And these GPUs, they have been optimized to draw points and rasterize polygons very efficiently, right? And this is, I think, one good example of bringing people from different areas together, right? In this case, using computer graphic techniques and insights to solve a database problem. So let me give you, some intuition for how this actually works. How do we evaluate the spatial aggregation on the GPU? So we start with the virtual canvas that is available on your GPU. And you start by drawing the points. And we draw the point on a pixel, and at that pixel, you start accumulating the count for the points that actually lie in that pixel. So you draw one, and then you update the count, draw another point, update the count, and you keep doing that. Now we have 2 points in that same pixel, and you do that for all points, right? Once we have all the points, we draw the polygon and we rasterize, which essentially is color the pixels that lie inside the polygon. And as we do that, we aggregate the count for all the pixels that are inside the polygon. So here we have 0, then we have 2, continue 2, 3, and so on. And after you rasterize the whole polygon, after you color all the pixels, you end up with the actual count for points that lie in that polygon. So what are the advantages of this approach, right? So one is that we actually exploit the native support for these drawing operations that are very efficient on the GPUs. Now we can do the aggregation and join operation in a single step without the need to materialize the intermediate results, right? And no longer we need to do the expensive pointing polygon tests, right? So this is great, but there are a few caveats that I'd like to point out. One is that as people that work with GPUs and graphics know, the rasterization process can actually introduce false positives and false negatives, right? For many applications, this is not a problem. And here's an example where we have an approximate heat map and the accurate heat map of the taxi pickups in New York City. And just, by eyeballing this, you cannot see any difference, right? So some applications can actually live with these approximation errors. However, if you want to reduce the error, you can simply adjust the resolution, right? By reducing the pixel size, you can better approximate the polygon outline, right? And that's what's inspired us to develop a variation of the approximate raster join that can actually bound, you can actually, depending on your application, you can actually specify what an acceptable error is. Right? And for people that require exact responses, we also designed this accurate raster join that uses the raster join operation. But then for the points in the boundary, we perform pointing polygon tests. Right? So what can we get with this raster join? And the idea is very simple, but the performance results, at least to me when I first saw them, were quite impressive. So we did a detailed performance evaluation, and here's just like one example, and that's showing the results for executing, this spatial aggregation over 800 million points crossed with 260 neighborhood polygons. And we executed these queries on a laptop that has an NVIDIA GTX 1060 GPU, right? And in the first plot here, we're showing the speed up over a single core CPU, right, with increasing data size. And what we can see here, and we have the bounded, the bounded raster join on the top, is that you can attain an over 300 times speed up compared with the multi-CPU implementation that we used as baseline, right? So you can see the potential gains that you can get from using the GPU. And in terms of execution time, is that's what this plot on the right shows. Here we have, the actual execution time in seconds, again, for varying sizes of data. And here we have the numbers for the raster join, right, for 400, 500, up to 868 million polygons. And you can see here that, to execute the spatial aggregation over 800 million trips, it takes just 1.1 seconds, right? So what is the takeaway here? So the first is that for the first part, which is, you need usability, but, usability and performance go hand in hand in order to support data-driven exploration. And to do this and to combine usability and performance, you actually need to combine techniques from visualization, computer graphics, HCI, and data management, right? And another important takeaway here is that, these GPUs that are available on all desktops and laptops actually can have a transformative effect in democratizing data analysis, right? So here we show that we really don't need big iron to analyze big data. Okay, granted, big is in the eye of the beholder, but say big and a few billion records, right? You can actually do that in your laptop. And, in our group, we did a lot of work to solve different, data management problems, spatial data management problems using the GPUs, not only the spatial aggregation, but we worked on spatial selection for keywords, for numeric data, and lots of other people have also worked on this and attained similar results, that GPUs can actually give you big gains and enable the, the analysis of big data in commodity hardware, right? One thing that we'd like to try is, what if now we have a GPU cluster, right? So we're likely to do much better. But what are the challenges here, right? And the challenge is that developing code for GPUs is difficult. And then it's not surprising that what we've seen in previous works, even our own, is that these are all one-off solutions that consider a specific operation. And it's difficult to reuse these across different queries, as well as when we have different geometric objects. Like, for example, you can develop something to do point and to do point selection, polygonal selection of points, right? But if you want to do polygonal selection of polygons, then your code isn't likely to work. And another limitation here is that most of these implementations, including our own Raster Join, are hardware specific, right? So our code was developed for CUDA, so it works for NVIDIA, but doesn't work for the other GPU vendors. So the next question that we asked ourselves is, can we abstract away this complexity, right? And actually build a unified database engine that uses the GPU to support a rich set of spatial queries. And this is what we did with the work that we presented this year at SIGMOD on GPU-friendly data model and algebra, right? And the key idea behind this is the same insight that we had for the raster join, and use the graphics pipeline and translate these spatial queries into drawing operations that can be efficiently executed in the GPU, right? And, the data model consists of what we call a canvas that provides a uniform data representation for geometric objects. And we also developed an algebra of simple composable operators that are optimized for the GPU and operate over these canvas objects, right? And one big benefit of this approach is that it's completely hardware agnostic. So you can have a single implementation that will work over multiple GPU, NVIDIA, AMD, Intel. And one thing to point out is that, we talk about an algebra, right? And here it's slightly different than, relational algebra, in the sense that our algebra was actually designed for use by the developers to build the spatial queries. And I'm going to discuss this in more detail, right? So let's first look at the canvas representation, right? So again, the idea is that you're gonna represent the data as the drawing of the geometry that corresponds to the data, right? So you can think of it as geometries in the world coordinate space in the graphics pipeline. And that makes it easy to efficiently apply these computer graphics operations on these objects. And if you want to have an analogy, a canvas in our model is analogous to a tuple in the relational model, and it's formally defined as continuous functions over R2. So you have a canvas that go over from a point in R2 to S3, and this S3 is where information about the geometry is going to be stored. Right. So very quickly, give you some examples. Suppose that I have a list of restaurants in New York City, records in my relational database, and each restaurant has an associated latitude and longitude. Right. So we would actually represent each of these points as a canvas in our data model. Right. So you have one restaurant here and another restaurant there, covering, the point 10, 10 in R2, and this is, the information about that geometric object. And you can also, represent polygons using the same model, right? So in that case, the entire region covered by the polygon has a valid function mapping, right? And the model also supports complex geometries made up of more than one primitive. So for example, here we have ellipses, lines, polygons, and so on. So in terms of the algebraic operators, I'm not going to get into the details. I would point you to the paper. But just to give you an idea, these are simple operations that are adapted from common computer graphics operations, like transforming objects, changing the values of these geometric objects, masking to filter regions of the canvas that you end up only with regions satisfying a user-defined condition, or blending two different canvases in one, or dissecting points from one canvas and creating multiple canvases. Right. So let me just give you a simple example of how these operators actually work. So let's look at the spatial selection query, that I showed before. Finding all restaurants that lie within a neighborhood polygon queue, right? So in order to answer these queries, you can have this simple plan where you start with the two canvases, one corresponding to the points and one corresponding to the query polygon. You apply a blend operator and you put them all in a single canvas, and then you apply mask to actually find the intersection. In this case, there's a single point that actually lies inside that polygon, right? And what is interesting is that even if we have now a different information for my restaurants, instead of points, I represent them as polygons, say, corresponding to the buildings where the restaurants are located. Right? You can actually use the same plan. You do the blend and then you do the mask, right? So you have different geometric types, but you still have the same plan, right? So what does this algebra allow you to do is that, by combining these different simple operators, you can actually express different spatial queries. And here I have some examples that does selection of origin destination data using multiple polygonal constraints, and even the raster join that I described earlier in the talk. Right? And the benefit here is that you can have a single representation for your data model in algebraic operators. And the programmer, the database designer can use these to actually build and support other spatial queries. And in our paper, and one other thing is the fact that, now everything is going to run on any GPU hardware. Right? And as we show in our paper, we can support rich set of spatial queries, selection, joins, aggregations, KNN, selections and joins, as well as some computational geometry queries. And we can do so by writing no additional GPU code. So as systems folks, you can actually ask, what about the performance, right? And what, does this actually work in practice? And so far we have done a preliminary performance evaluation where we compared an implementation, a prototype implementation of our spatial algebra running on a laptop against, GeoSpark, which is a spatial engine that works on Hadoop-based clusters, right? And in our experiments, we actually used a cluster that has 17 nodes. And here are the results. And here we're doing spatial selection queries using different polygons with different complexity. And on the left, we have the times, the query times in milliseconds, and note the scale here, 10, 100, it's by 10 times each point in the axis, right? And here for, a query that takes into account over 1 billion taxi trips, and this is a point data set, and does spatial selection using polygons from New York City neighborhoods. What we can see is that the times for the spatial algebra are significantly smaller than what is running on a laptop, are significantly smaller than those attained by GeoSpark running on 17 nodes. And that's also true for another data set, and in this case are tweets, over 2 billion tweets. And here the polygons, we got them from US counties, right? So we get here anywhere between 10 and 300 times speed up compared to GeoSpark. I would also like to point out that, these are, very good cases for our approach. There are also cases where our approach is actually on par and attains response times that are comparable to those of GeoSparks. And this is the case for this other data set that is smaller. Actually, it's only 114 million buildings, and this is a polygonal data set. And these are buildings worldwide that we obtained from OpenStreetMap, right? So anyway, so I think I misspoke. So the speed up is actually from 2 times to as high as 108 times compared to GeoSpark, right? But this is very preliminary work, and there are a number of open questions that we still need to answer, right? So I'd first like to point out that this algebraic model are compatible with the relational model and can be easily incorporated into existing relational systems. But in terms of open questions are, yes, I think that there's great promise of deploying this in a cluster environment. But there are questions like, how do we partition the data? How do you index the data? How do you optimize these queries? Some of these questions, the folks that do GeoSpark, who has now become an Apache incubating project called Sedona, is that they started to look at this, but this is a difficult problem. And when we were doing our own experiments, we noticed like very large variations in performance for GeoSpark when we changed this partitioning strategy, right? We had queries that took anywhere from 20 minutes to 4 hours, just depending on the partitioning strategy used. So there's a lot of work to be done in terms of scaling up and deploying this on a cluster. But I see great opportunity here to support the processing of very large volumes of data, and in particular the support for large volumes of streaming data that these kinds of techniques enable at this point in time. I would also like to point out that where I showed you that Urbane supports this three-dimensional view of urban environments, right? And one of the goals that we have for our research is, how can we actually support, extend our algebra to support 3D data, right? And if we look at our canvas representation, it can be easily extended to support the 3D primitives. But the operators that we use do not have a straightforward implementation using the GPU. But Harish, who is actually Harish Doraiswamy, who is actually the person who did this work, tells me that this new native support that GPU cards have for ray tracing are likely to make it possible for us to support these 3D spatial queries. Right. So, I'd like to close this part of the talk with, our vision, right? So where do we want to get? Where we want to get is, to having spatial query engines and these visual analytic systems that enable both 2D and 3D analytics for all, right? How do we democratize the large scale, exploration of spatial data in urban environments? So I don't know if we want to have questions or if we leave, I forgot to ask to the end. Sharam?
Maybe it's best to leave it to the end.
Okay, right. So let me move then to the, to the second part of the talk, which is how do we ensure reproducibility and build trust for results that we derive from, these computational processes and computational pipelines, right? So as I said in the beginning, one big challenge that we face is that in exploratory analysis, we have to go through this iterative process. And it's a long, arduous process, and many things can go wrong, right? So it's, it's extremely important that you are able to assess the validity and build trust in your results. And this is particularly important now that we have so many people that have so many different backgrounds and knowledge in different areas, right? I may be a computer scientist and I don't understand very well about statistics. I am a domain scientist and I don't know exactly what are the right libraries that are not buggy that I should use in my pipelines, right? So it's now, even more important to have mechanisms that enable you to assess the validity of your results, right? And to do that, there is a key requirement. And the key requirement is that we maintain detailed provenance of all the steps that we followed, right? And it's only through this provenance that we can reason about the steps we followed and in the end, be able to reproduce and debug these steps. Right. So over the years, with my group, we have done quite a bit of work on methods as well as systems that aim to support users both in capturing provenance and using those information to help them build trust as well as streamline their analysis. And one example is the system that called VisTrals, which is an open source system that enables data explorations through workflows, right? And a while back, workflow systems were, the key solution proposed for provenance and reproducibility, right? And the reason is that, yes, you generate your plot, and if you use a workflow system, you have your beautiful workflow that, later you can rerun and regenerate your plot, right? But what we argued is that, although this is, extremely important, it's also very important to keep track of how your computations and your workflows evolve over time. So in addition to keeping, your workflows, you should also keep track of how you change your workflows and your computations as you pose and test your hypothesis, right? So the key idea, novel idea behind VisTrals, you can think of this as kind of like GitHub on steroids, is essentially that you keep the change history of your analysis, of your analysis, right? And if you keep this history, all these different steps, not only you can support reproducibility, But we've also shown that this additional information can actually be used to streamline data exploration. First, it can support reflective reasoning, which is, allowing people to backtrack and try different hypotheses, but at the same time, not losing context or forgetting where they, the steps that they went through. Right? It also gives you a reliable way of comparing data products, not just the results, but the actual steps that contributed to the results. Right? It also gives you a reliable mechanism to explore parameter space. You can, look at what would happen if you use different parameters in your computation, and you can even explore different kinds of computations in this exploration, right? And last but not least, it also enables knowledge reuse, right? And here's one example where we can use this information to actually create visualizations by example or by analogy. And here's how this works, right? You can actually build a VTK visualization toolkit pipelines that look like this to smooth three-dimensional objects, right? That you transform an object like this into a smooth object, right? I hang out with these people, but I would not be able to build such a pipeline, right? But once we have a history of lots of these kinds of transformations, right? We can actually, if we have other three-dimensional objects like this, right? We are using this provenance, the trail from previous explorations, we can actually generate the smooth objects by analogy. I can say this is to this as this is to, and then we can use this history to generate and automatically apply patches to the workflows or pipelines that are used to create these different images here. Right? So VisTrals was, extremely successful. It had, thousands of users, and amazingly enough, there are people using the system to this day. But it had one big drawback, which is to reap all these benefits, you actually have to adopt the system and do all your computations in this new environment, right? With the goal of broadening the adoption of, reproducibility and enabling provenance capture for wider audiences, we started to look at different mechanisms to do this, right? And we developed additional systems, and here's an example of two of them that attempt to do just that. So one of them is ReproZip. And ReproZip deals with the infamous problem of dependency hell, right? So you do all your work, your experiments, your papers accepted to SIGMOD. Now you have to send that to reproducibility evaluation. And how the hell are you going to gather all that you need, all the libraries, all the input data, everything that you need so that the reproducibility evaluation committee can rerun your experiments. So what ReproZip does is that it sits at the operating system level and automatically tracks and packs all these dependencies for you, right? And the other system called No Workflow was actually developed to track provenance for Python and Jupyter notebooks, right? So again, here the new idea is, how do you make reproducibility easy, right? And to work in your own environment, right? And these systems, again, they got lots of users, they got lots of uptake, but there are limitations, right? So ReproZip only runs on Linux, and No Workflow only works for Python. And I'm gonna touch back on this issue in a few slides, where I see that there's a lot of opportunity for systems work to actually contribute to better solutions, general solutions to making reproducibility easy, right? But reproducibility and capturing provenance and attaining reproducibility are great, but they're not the end goal, right? So reproducibility is just a means to an end. Why? Because it's the key ingredient. It's what's necessary to verify and build trust in your results, right? And in particular, to debug your computational pipelines. Because what we've seen is that, again, everybody's using computing and data to obtain results. And if you look at big companies, you see, lots of these computational pipelines developed by different groups that are deployed throughout the company. And the problem arises when you get a result you don't understand, or when one step of these pipelines fail. How do you go about finding what caused that failure, right? And you can only do that if you have provenance. And as I'm going to show, it's also very useful to have the ability to reproduce these processes, right? To debug these complex pipelines. So what is the problem here? Right? So the problem is, you're given a computational pipeline, and this could be a simple pipeline or one that has multiple components that are distributed and executed in different computational environments. You have the provenance of, these previously run instances of your pipeline, and you have a way of telling whether the pipeline succeeded or failed. Right? So here's a concrete example of a machine learning pipeline, a template that reads some data, splits that data into train and test, applies an estimator, and then computes the result, right? So, and the idea here is that you use this pipeline to identify what estimators are best for different problems, right? And here you have the provenance of this pipeline for executions that consider different data sets, different estimators associated with the library versions of scikit-learn that these estimators come from, and the final score for the estimator. Right, and in our case, we say that the pipeline fails if the score attained is less than 0.6. Right. So one great thing is that if you have provenance, by analyzing these the instances, information about the different instances, you can create some hypotheses for the failure, right? So in this case, we can easily see that all the instances that failed used gradient boosting in library 2.0, right? So this gives me an idea of where to look for. But then you can ask, are these the actual causes of failure, right? And to ascertain and to answer this question, what you actually need to do is to try additional instances. So for example, if I now run my workflow again, and now I keep my gradient boosting, I keep my same data set, and I change the library and I rerun, now I see the success. Right? So the pipeline now succeeds, and now I can see that the problem is not with gradient boosting, it's actually with the scikit-learn version implementation of gradient boosting, right? And this is actually a real example that we found while working on this problem, right? So yes, so if you have provenance, it's great. It's much better when you're able to run new configurations. But the problem is that, you can run an infinite number of new configurations. And the question is, how can we effectively select new configurations to try that can help us generate these root cause explanations for bugs in pipelines, right? So we actually developed a number of algorithms that attack different aspects of these problems and leverage the ability to re-execute a given pipeline to build more robust explanations for failures, right? So one of these algorithms is what we call shortcut, and we showed that it is able to find root causes very fast in linear time with respect to the number of parameters, right? And of course, the caveat is, it works in linear time if the root cause has a particular property, right? If you have simple root causes that are either, single root cause for a problem or conjunctions of root causes, right? And we also have a, more expensive algorithm that you can apply to generate more complex combinations of partial configurations of parameter combinations that are root causes for problems, right? I won't have time to talk about this in detail, but you can see in our paper that our approach actually attains very high precision and recall in terms of finding these problems, right? One note is that, yes, this can be expensive in the way, depending on the pipelines that you execute. And the way that we have dealt with this is by, simply running instances in parallel, right? Because, in this case, we have an embarrassingly parallel problem where all these different instances are actually independent. Recently, we've also collaborated with a group in a large software company where we integrated BugDoc with their proprietary workflow system, right? Was a nice validation of this work in that, our algorithms were actually able to identify problematic configurations and generate root causes that were helpful for the folks at the company to actually identify and correct the bugs in the pipelines. Right. So the takeaway here is that, provenance and reproducibility are, essential ingredients to build trust and explain results produced by computational processes. We've seen recently a lot of work that aims to explain, machine learning classifiers, right? But I see here a great opportunity and a great need to, explain complete computational processes, right? Because machine learning is just one piece of, these data science pipelines, right? One not so, how can I say, good reality is the fact that, although everybody knows that reproducibility is important, not everybody actually produces reproducible results and follows reproducibility best practices, right? And there's actually a report that was produced by the National Academies that was published last year, and I was honored to be part of the group that generated that report that talks about this in detail, right? And I think one of the findings that we have in the report is that we really need tools that make it easy for people to produce these reproducible results, right? As a colleague of mine from Berkeley says, it should just be part of your computational environment, and you shouldn't have to do anything else to actually to obtain provenance and get reproducibility, right? So this is part of my dream is, to have provenance capture and reproducibility supported for all tools and computational environments. Right. And I'd also like to point out that, lots of people, including in this report, we talk about, in this NAS report, we talk about reproducibility as being something that is important to science and for scientific progress. But, reproducibility is actually very important for each one of us, because by making our experiments reproducible, it forces us to document all the execution pathways. And this not only helps newcomers to our group, it also helps us to build trust in our own work. And also some other carrots that people get when they work in a reproducible way is the fact that, by making your work reproducible, it helps with dissemination and reuse, right? And there's actually preliminary evidence that papers and work that are accompanied by, the source code and data used, it greatly impact their visibility. They get more citations and also improve their research quality. So, to conclude, I think that, you know, as I told you, a big part of my research actually aims to empower domain experts to perform data exploration, and does require, you know, new methods and usable tools that enable them to interactively explore data and assess and debug their results, right? And thus demands interdisciplinary teams and collaborations, not only within different researchers from different areas in computer science, but also collaborations with domain experts, right? So as I showed in these projects I described, we combine visualization, data management, computer graphics, statistics, right? And, you know, our work solves domain problems, but we also were lucky enough to kind of like fall into this virtual cycle where we can solve disciplinary solution problems, right? And we can use disciplinary challenges to actually derive new computer science problems, right? And I sincerely think that, you know, our areas, data management and systems, we are very well positioned to have a tremendous practical impact in, you know, democratizing data exploration and the use of, and the responsible use of data and computation. So with this, I conclude my talk, and I have to thank all the different people that contributed to this work. In fact, this work was actually mostly done by them, and I'm one of the contributors and the messenger. And also I thank my funding agencies. Okay, thank you so much, and I'm happy to answer any questions you may have.
Thank you so much, Juliana, for a wonderful talk. So here's a question for you from Xiaojing Lu. Writes, thanks for a very interesting talk. ML is one of the components in the pipeline, but it tends to evolve or be tweaked to handle new data to improve on its accuracy. In this case, how do you maintain model data provenance?
Right, so I think that the same ideas that we used in VisTrals are applied here, right? Sure, is that, you know, you need to keep track of the changes that you make to your machine learning pipeline, the different hyperparameters that you use, the different task split data, right? So all that history has to be maintained so that you can, you know, in the end, figure out what exactly you have done and how you got to the results. So you know, while, you know, when we're doing VisTrals many years ago, we focused on visualization, I see a direct parallel with the challenges that people are facing now in machine learning.
Very good. I have a few questions of my own. One of them is that in the context of the first part of your talk that you gave, the new iPhone that's coming out supposedly has 4 or 5 GPUs in it. Have you considered extending your framework, your approach from a laptop to a mobile device?
That's a very good question, and that's something that Harish has mentioned to me, right? You know, I don't know the details of you know, the GPUs in the phone, but you know, that's a very interesting opportunity. Although, right, when you're doing visualization, having so few pixels will likely limit your ability to do this kind of exploration. So for some problems, it may work well. But for others, I don't know. And the other thing is that you need lots of memory, right? So I don't know how much memory is going to be available there, but likely you're going to be able to do on phones what you're not able to do on desktops a few years ago.
Sergius writes, inspiring talk. I'm wondering if the proposed graphics perspectives can also improve the spatial I/O efficiency indexing in addition to the computation speed.
Right. So we've actually done prior work where we use GPUs to build indices. So this is a paper that we had in ICDE 2000, and now I forget, right? Where we actually use the CPU to implement a KD3, off-core KD3 index. that, greatly improve the performance for spatial selection. So this is actually possible, and we've done it, right? But even for the spatial algebra and the spatial query engine that we are building, there's lots of challenges in terms of what kinds of indices are needed and that can improve the, that use GPU and that can improve the execution time, the performance of these queries.
Yan Cheng Wu writes, great talk. A quick question is, can the algebra and data model be efficiently applied to support queries that also incorporate textual data along with the spatial temporal data?
Right, so we haven't really looked at that, right? But in previous work, we actually, so I talked about this spatial index for spatial selection. So we did that for numeric data, and we also did for textual data. And the way that we did it was by representing the textual data as numbers. Right? So right now, if you can find a good mapping for your textual data into numbers, it could actually be supported. But I have to say that we haven't really thought about this in detail in the context of the algebra.
This is my own question. Juliana, how do updates impact the algebraic representations? For example, if a taxi moves away from a region or there is a new tweet, does the algebraic representation
Right.
change?
So maybe before I do that, let me just go back to the previous question, right? So so in terms of, so the algebra itself is operating on just the spatial attributes of the data, right? So as I showed in the example, maybe I showed too fast, you can have information in a relational database in a table, right? And that, say, a restaurant or a neighborhood, right, is associated with a geometry, the location of that object in space, right? You can still do whatever, ask whatever queries about the textual part of those objects using our relational database, right? And only delegate the spatial processing, the selections, the intersections, and so on to the spatial query engine, right? So this is where comes the power of integrating this algebra with a relational database system, right? So in terms of your question, and now you're gonna have to remind me very quickly.
It was in the context of updates.
Oh, right.
If the taxi moves, what happens to the algebraic representations that you're talking?
So if the taxi moves, I mean, if you can think of this as kind of like streaming data, right? So it shouldn't affect, I mean, it's, so right now we didn't really design the algebra to be, efficient for streams, but lots of the operators actually would work well in a streaming situation, right? And I think that the advantage here is the fact that, everything that we're doing is in real time. And in this case, we don't even have like pre-built indices, right? So if there's new data coming in, they can just be executed, they can just be evaluated, through the algebra. So there's no extra overhead.
Our general chair, Rodrigo, writes, you showed that you can run a lot of computation locally, but in some cases, moving data to the devices would be prohibitive. How do you reason about the placement, movement of data and computation?
Right, so I think that this is a great question, right? And in our paper, we actually discussed this issue at length, where, most of the time when I show those performance results, it's, very short execution time. And most of that is actually transferring data between the CPU and the GPU, right? So data transfer is a big problem, internally, GPU and CPU. And the light in the end of the tunnel is that, these new versions of CPU cards are, more and more optimizing these transfer, and it's getting faster. So one good thing for us is the fact that as the hardware gets better, our techniques automatically become faster, right? But if Rodrigo was actually referring to transferring data, say I have big data sets at different sites, right? And I need to bring them to be processed. That's still a big challenge that I think that the systems community can help. And one particular challenge there is even when you have all these different data sets in the same cloud environment, how do you place those data? How do you partition those data so that you can efficiently run these queries? I think to me that's a big open question, in particular for spatial data.
We have several more questions. We are running out of time quick. Juliana, if you could be efficient in answering this question, I think this is the last question. What do you think are the factors that limit people from incorporating reproducibility in their work from your study?
So I think that there are a number of factors. I think one is just that people don't know better. People don't know. I mean, it used to be the case that doing reproducible work was difficult, but nowadays there's lots of tools. You have virtualization. There's lots of strategies that you can use that make this a lot easier. Right. So I think that the one answer is that we need to better inform people of what is available and how they can attain that. I think that the other challenge is that although we have tools, as I have alluded to, one challenge is that there are gaps, right? So some tools work for Linux, don't work for Windows. They address a particular subset of problems, right? So I think that one big challenge that we have is, how do we actually, as I mentioned in the slide, how do we make provenance capture and reproducibility, available everywhere in all tools, in all operating systems, in all computational environments.
Sounds great. We are over time. Juliana, thanks again. And this is the end of the keynote.
Thank you
very
so much. Thank you, the attendees. Thank you, the organizers. It was a pleasure.
Wonderful.
Thank you.